Hey Method students, another past exam question here. This one's a bit of a doozy, so let's get stuck into it and I'll try my best to explain the steps as we go. So this one says, let f be a differentiable function defined for all real x where f of x is greater than 0 for all values of x between 0 and a. Okay, so we've basically got a continuous smooth function where the function values, the y values are positive over this interval. If the integral from 0 to a of f of x with respect to x is equal to a, then this messy looking integral is equal to, and we've got to pick the right option. Okay, so this is the classic, let's start by maybe just drawing a picture and seeing if we can kind of break down what's going on. So first thing is, well, we've got this sort of function f of x. We don't know much about it other than it's positive over this interval from 0 to a. And we're being told that the integral over a particular sort of region is equal to a. So let's just try to sketch that and really just think of like some basic type of function for f of x. So I'm going to just imagine that f of x, maybe it's like a parabola, but it's just the positive, the sort of increasing part of a parabola. So I'm going to imagine that that's f of x, and this is the point where x equals a. Okay, and this, try to sort of use some different colors here, this area that we're given, right, from x equals 0 to x equals a, is actually equal to a. All right, so this red area equals a. Okay, so let's just keep that in mind. This just sort of helps us work out what's going on, especially later when we now try to kind of go, all right, well, let's try to deal with this thing, because this is the thing that we're trying to find the value of. Now, there's a lot going on. We've got a 2 in front. We've got a plus 3 now included with the function, but we've also got this f of x over 5, which is obviously going to do something to our function. So maybe before we get too far along the line, let's actually just think about, well, how can we use what we know about integrals to kind of deal with this a little bit? And one of the things that we know is that we can actually, if we've got the sum of two things inside of an integral, we can separate those into two different integrals. So I'm going to call this 2 times, and now the whole thing's still going to be multiplied by 2. So I'm going to split this into the integral from 0 to 5a of f of x on 5 with respect to x, plus the integral from 0 to 5a of 3 with respect to x. Okay, so now at least we know, well, that second part of the integral, we're going to be able to work that out. We can anti-differentiate 3 and we can sub in those terminals. That bit shouldn't be too bad. We're still going to have to get our head around this, right? This part here, this sort of, this f of x on 5. So let's think about it. With our transformations, we know that when a function goes from f of x to f of x on 5, well, that really is, I'm going to make a note of it down here, going from f of x to f of x on 5 is a dilation, and this is our dilation away from the y-axis. It's a dilation by a factor of 5 away from the y-axis. Okay, because remember that with our dilations away from the y-axis, if the dilation factor is n, then the function becomes f of 1 over n times x. So if the number in the function is 1 over 5, then the dilation factor is actually 5. So essentially, when we come back to thinking of our picture, if this function here is f of x, well, f of x on 5 is just going to be this same function, but stretched 5 times further away from the y-axis. And I'll try my best to draw it to kind of perfectly to scale, but obviously this is just a by hand sketch, so it's not going to be dead on. But we're going to get this function that now all these function values along this curve are going to get 5 times further away from the y-axis. So we're going to get something resembling this. All right, so if f of x has been dilated by a factor of 5 away from the y-axis. What I've tried to do is show that this point here and that point there, like this point's now 5 times further away from the y-axis. All right, so this is our graph of f of x on 5. Okay, and the other thing that's going to happen is that if we had this if this function was drawn from 0 to a, well, this dilated function is now from 0 to 5a, okay? And that's good because those are actually the terminals that are on this integral here. Remember, for this part, we're just thinking about how to deal with this integral, right? So what does that mean? Well, if I'll try to use a different color here to show that it's a different area. So if we sort of shade in this part here, the area under the function f of x on 5 from 0 to 5a. Well, if I've taken this area, this red area, and all we've really done is made the area 5 times longer. It's got the same height, but it's now 5 times longer. Well, that's just going to increase the area by a factor of 5. And so in other words, blue area is 5 times bigger than red area, which means blue area equals 5a. Okay, so going back to this expression now, we've actually got, with a fair bit of thinking graphically and getting our head around it, we've got that this integral from 0 to 5a of the function f of x on 5 with respect to x is just equal to 5a because it was 5 times the original area. Okay, so that part's 5a. This second part was the bit we said, well, we still have to anti-differentiate 3, and the antiderivative of 3 is 3x. Terminals are 5a and 0. All right, and so, well, 2 times 5a plus, now obviously when we sub in 5a in place of x here, we're going to get 3 times 5a, which is 15a. When we sub in x equals 0, we're going to get 0, so that's just evaluating the definite integral. We get 15a take away 0. And so after all that, we've really just got 2 times 5a plus 15a, which gives us a total of 40a. And hopefully that's going to be one of our options, and yes, it is. It's option D. Whew.